All right. Okay, let's jump into it. So we are here today to talk about moons of the solar system because yeah, I thought planets are getting way too much attention and the moons are often getting the short end of the stick, so we're going to rectify that today. So we're going to talk about a short introduction, what's a moon and kind of what do moons do. And then we'll go visit the various planets of our solar system, to see what's going on there with regard to their moons. And then if we have time, we'll talk about something I call the moon alternative, and then we'll wrap it up. And so, yeah, let's kind of jump into the introduction here. So, astronomy has a lot to offer, right? There are all kinds of beautiful things that you can see in the sky, like, stars, star clusters, nebulae, planets, other galaxies. These are all really neat. And today we're not going to talk about any of those, right? Because we are here to talk about moons. And just to give you a reference here, right? So today, yeah, we're doing this particular talk in our Astro 101 series, but we actually have a whole bunch of other material that we cycle through. So if you like today, or even if you don't, you can try one of these other ones, and there may be something else here that you like. And there's some more that we're developing. So in the future, there'll be some new material coming up that nobody has seen so far ever. All right, so today is about moons, and there's a lot more to moons than you might think, right? And ask questions as we go through this. And if you're lucky, I or one of my co-hosts will know the answer. I do want to be clear, I'm not an astronomer. I just do this stuff because I think it's interesting and fun, and we just like sharing. So, but do ask us questions, and you can test our knowledge. And an assignment I have here is, pick something from this talk and maybe ask somebody about it later, especially if you come to one of our star parties. That could be a great opportunity to ask someone there about, something that you've taken away from today's discussion here. So, okay, so what's a moon and what are they doing anyway? And so one key question is this a moon? And I realized that with this slide, I'm dating myself, right? I'm actually wondering how many folks in the chat even recognize this picture because I realize I'm old. But let's see. So, you know, anybody remember, this scene from Star Wars? It's from many years ago, right? But of course, we have the Millennium Falcon, coming up and seeing the Death Star for the first time, and they're going, "That looks like a moon, but it's not actually a moon." And bad things happen after that. So, um, so the Death Star was not a moon, but this thing, is this a moon? And so the interesting thing here is that, yeah, Star Wars' Death Star is not a moon, but this thing that doesn't look all that different actually is a moon. And we'll visit it again a little bit later as we go through our talk today. So let's be a little more formal about this, right? What is a moon? So a moon is a natural satellite. And, for that to make sense, we should make sure we define the word satellite. So a satellite is an object that's orbiting some other object, right? And orbiting here means kind of, zipping around it, circling around it. Um, but the object that it's orbiting is not a star. Okay, so a satellite is something that orbits something else, but that thing at the center is not a star. And a satellite may be artificial, like a communication satellite around Earth, or it could be a natural satellite, like our moon is. And so, what are those not moon things? Let's be clear about that, right? So a star is a sphere of mostly hydrogen that produces energy through nuclear fusion, and thereby it shines, just like our sun did today, right? And will do tomorrow. And then planets are objects that orbit stars. So our Earth is a planet, Mars is a planet, and these things orbit stars, and they are not stars themselves. Okay, that classifies them as planets. And they're also massive enough such that they've shaped themselves into a sphere through their own gravity, right? So Earth is a sphere, Mars is a sphere. And further, they've managed to clear its orbital neighborhood of other stuff. And I'll explain that a little bit more in a moment. Because this kind of gets us to the question of, Pluto, right? You're probably all aware that, at some point in the past, Pluto got demoted, right? It used to be something we call a planet, and then everybody became sad when the astronomers said, it's not a planet after all, we'll just call it a dwarf planet instead. And so, what does that mean, right? And for that to make sense, we need to think about orbital paths for a second, right? So here's our sun in the middle of our solar system, and you have our planets. Here's the Earth, going around in their orbits. And by the way, this is a beautiful artist rendition, but in terms of size and scale, it's really all wrong, and we'll see a slightly more accurate representation in a moment. But you can see that here there is some space junk in the asteroid belt, and that there's also just miscellaneous space clutter out here. But each of these planets has a really nice clean orbit, right? Its path is devoid of other loose clutter, right? Other junk. And so this is the asteroid belt, right? This is the Kuiper belt, and if we look at that in a slightly different way, you can imagine it like this. The Kuiper belt is actually this really big region of clutter, and Pluto is this thing right here. So Pluto's actually zipping through the Kuiper belt, right? Its orbit is not nice and clean like the Earth's or Jupiter's or all these other guys has become. And so this is one of the criteria that Pluto then does not meet to be a planet, right? Its orbital path has not been swept clean of stuff, right? Pluto is too small. It's not massive enough to have cleaned up its neighborhood. But yeah, so we call it a dwarf planet as a result, right? But dwarf planets can still have moons, and for today we'll include Pluto. If we have time, we will visit its moon as well. So again, just to make sure that we're really clear on how this all looks, right? So a basic planetary system model, has a star in the center, and then there would be a planet out here like our Earth, and that can then orbit the star. And then we said a moon is a satellite that orbits something that is not a star, and so here you go, right? So here we have a planet like our Earth, and then the moon, and our moon or some other planet's moon, can be orbiting here. Um, and so these things can arrive or occur in various types of complexity, right? So at the center of a planetary system, there could be just one star. This is like our home here, right? We have one sun in the sky. So there's, one star at the center of our planetary system here. But it's possible to have multiple stars. We would call this a binary star. They're actually two stars that are gravitationally connected. And we actually see many systems like this when we look through our telescopes into the distant night sky. Turns out that more than half the stars we see out there, star systems that we see, are actually multiples, binaries, or sometimes even triples or other fun things. So in a way, our solar system is actually the minority that our sun is a single. You know. And then stars can have multiple planets. Our solar system has 8, not including Pluto, because we just said it's now classified as a dwarf planet. And then planets can have multiple moons, possibly dozens. And you might ask the questions like, well, can a moon have moons? And the answer is actually yes. You could have a system that looks like this, where this moon actually has its own little orbital companion, and so this moon could have its own little moon. That could happen. And now, where do moons come from, right? How did our moon get here? How do other moons get around their planets? And there are multiple ways moons arise in planetary systems. So, and to answer that, answer how that works, we should first ask, well, where do planetary systems come from? It's like, well, so a recipe for a planetary system is to take like a giant cloud of gas and dust, and we let the cloud collapse into a disk, and we could have a separate conversation about why it's actually a disk. The short answer is because of conservation of angular momentum. If that didn't make sense, don't worry about it. But yeah, so our gas cloud is going to collapse into a disk, and then in the center of that gas cloud, uh, gravity will pull hydrogen gas together, and ultimately a star forms there. It ignites through nuclear fusion and then shines, generating energy for that, this new planetary system. And then we wait for the dust that's orbiting the star to coalesce into planets. Sounds easy, right? And here's kind of a representation of this in picture form. So there's a big, gas cloud here. That gas cloud collapses into a kind of a flat spinning disks, a flat spinning disk. Okay. And you will have over time collecting a lot of hydrogen gas collecting in the center here. When you have enough, a star will have formed and will have ignited, and that energizes the whole system here. And then furthermore, as this proceeds, planets will coalesce out of all the other junk, that's in the outer parts of the disk. And then over time, the system kind of cleans itself up and it becomes nice and neat, like our solar system looks today. And let's see, actually, we will skip this video today. But then we can ask, okay, what forms a moon, right? So now we formed ourselves a solar system, with a star in the center and some moons around it, excuse me, some planets around it. How do we get moons into the picture? Well, moons can form in several ways. Okay, one can be what we call accretion. So, which is kind of like how the planets formed around the star in the prior story that we just told. So, accretion would mean that, yeah, there's just like a disk of dust around the planet, and the dust or other clutter in that disk can coalesce, stick together, and then, through gravity, pull itself into a firmer object, and that could become a moon around a planet. So, accretion is coalescing from dust around a planet, like a planet coalesces around a star. A moon can also be captured. Maybe it formed somewhere else, and then it flies by the star, flies by the planet, and the planet's gravity might, be able to capture that moon and pull it into the planet's orbit. Or it could be a fission event, meaning a breaking event, right? So maybe, first you just have the planet, but maybe if the planet is spinning really, really fast, and if it's not sufficiently strong enough internally, a part of the planet may actually break off, and kind of fly away for a little bit of a distance, and then become a separate object, a moon around the planet. Or you could have an impact. You have your planet, something comes again from the outside. So similar to capture, an object arrives from the outside, but it doesn't get captured kind of peacefully. Instead, it actually crashes into the planet and temporarily makes a big mess. But then, another body forms that is the moon, that new moon. And so the leading hypothesis for the formation of our moon, right, Earth's moon, is actually this impact hypothesis. So best evidence we have is, something hit the Earth a long, long time ago, made a big mess, and then, our moon formed from that mess. So a quick review, a moon is a natural satellite, and it's an object that orbits a planet or another moon. And planets may have zero, one, or multiple moons, and a moon may have moons. And then moons can form in a variety of ways, like we said just on the prior slide. So now what do moons do for us? Well, ours can look quite pretty. So this is a cool photo. It's actually a real photo, although the moon looks huge here, behind Lick Observatory. And while this is a real photo, this perspective, this huge moon was produced to some, photo trickery, right? So the moon is not actually that huge in the sky, but it does look pretty neat, right? So our moon is quite a pretty object. And hey, songs have been sung about it, and poems have been written. Um, but what has our moon done for us lately? Well, just a little while ago, it gave us tides, and we should talk about that a little bit. So tides, of course, are kind of the raising and lowering of the water level at roughly 6-hour intervals, right? If you live or have lived by the coast, you've seen this happen, right? Uh, and the question now is then, well, what exactly causes the tides? And maybe our first answer would be Aquaman, right? If we watch recent movies, Aquaman has a lot of power over the sea. But regardless of how attractive we think Jason Momoa is, well, he didn't actually do it, right? So Aquaman is not in charge of tides. Sometime in the past, people thought, hey, maybe it's Poseidon, the god of the seas, right? He causes the tides. Also the wrong answer. We know today, right, that the tides are a product of gravity and orbital motion. So, moons cause tidal effects, through gravity and orbital motion. So let's talk more about how this works, because this is actually really, really important when we think about moons in general. So we'll do a thought exercise here, right? We'll create ourselves a planet, something like the Earth. Boom, here is that planet for us. Now we'll give that planet water all around. So imagine it's just an ocean planet, right? It's just water all the way around the planet's surface. And then, we'll pop a moon into existence. So now here we have a little moon up here. And now gravity causes these two objects to attract each other, right? Any two things actually attract each other. So, if you're watching, me tonight here with a friend sitting next to you, well, you and your friend next to you actually have a gravitational attraction between you two. But our bodies are insufficiently massive for the gravity to be noticeable. It is just way too tiny to really matter in any way. But the Earth and our moon, for example, they're pretty big. So there, the gravity is quite noticeable. In fact, Earth gravity is what's keeping me in my chair right now, and it's preventing me from floating off into space. And so here then, right, we have The moon is, this moon is kind of pulling on the planet a little bit, and the planet is pulling on the moon. And that results in some, combined mutual attraction that's trying to pull these two things, together. Now, you might ask, well, if they're being pulled together, don't they crash into each other? And there's something else going on that's preventing that, and that is that the moon is moving, right? Is actually zipping around the planet in its orbital path. So it is taking a circular path around, and it's moving just fast enough that it can uh, essentially balance out the gravitational pull, by perpetually going around in an orbital path. And so, okay, so now let's focus on the moon's pull on the planet, right? So we just said the moon exerts some gravitational pull on the planet. And, um, we should think about that a little bit how gravity works. Gravity diminishes with distance. So the farther I get away from something, the weaker its gravity effect on me becomes. And um, so the moon pulling on the planet, right? If the planet were right here, it would receive a really, really strong pull. The farther away the planet is, the weaker the pull is. And that even matters if we just think about kind of these two ends of the planet, right? So the top part of the planet has a stronger gravitational pull from the moon than this bottom part of the planet. Here, the gravitational pull is weaker, just because overall the gravitational pull of any object diminishes with distance as we get farther away. And so we say that the planet then experiences differential gravity, right? So not everything is experiencing the same gravity from the moon, but it actually varies based on where you are. And as a result, then, yeah, so this part right here has more pull from the moon, and this part down here has less pull from the moon. And that causes something interesting to happen. Now, differential gravity actually applies to you too, right? Imagine, you're standing here on the Earth and there's a moon above you. Well, you know, uh, the moon actually pulls more strongly on your head than on your feet. But again, because we are relatively short compared to the diameter of the Earth or diameter of any planet, the difference is negligible. It really does not matter, but it is technically there, right? So technically, our moon is pulling a little bit more on your head than your feet, if it were overhead. But the difference is so tiny that we don't feel it, and it doesn't matter. But it's there. So yeah, you're short compared to the Earth. The difference is tiny, and we just don't feel it. But our planet is big enough to feel it. So what happens is that it actually creates bulges in the water. Okay, so here the water is pulled away from the planet, right? Because there is relatively strong gravity here. The water is pulled away, and then now this for me was always relatively easy to understand in my head. I could kind of visualize what's going on. Turns out we also get a bulge down here, and this one is a little harder to understand, a little harder to visualize. But I think the easiest way to maybe say it is down here, you can imagine that the planet is kind of being pulled away from the water. And as a consequence, we end up, with our planet having like these two bulges, one towards the moon and one actually away from the moon. And it's actually not just the water that bulges, right? The differential gravity also causes the planet itself to be a little bit pulled out of round, if you will. And let's look really, really closely, right? So again, here, this is kind of the before picture. But now if we consider the differential gravitational pull of the moon on the planet itself, it also gets pulled a little bit. It gets squished a little bit on the side and actually gets pulled up a little bit here and sticks down a little bit here. So the water gets pulled significantly, but even the crust, even the hard parts of the planet do actually get deformed. And our Earth does this too. Again, we just don't notice it, but it is measurable. So yeah, so now we have high and low tide, right? So if you're over here on this planet, right, you have high tide, and over here you have low tide, and the opposite sides, the same thing is going on. Now, planets tend to spin, right? So we have to add a little more realism to this. So now let's say that our planet is spinning, and uh, our Earth, of course, spins once every 24 hours, right? So every spot on the Earth experiences a high and low tide roughly every 12 hours, right? That's what happens here on Earth. Different planets might have different cycles, but the same idea would apply, elsewhere out in space. Um, but there's a little bit more to it here now, because the planet's spin actually drags the tidal bulges, right? So if the planet is spinning this way, it's creating some pull or drag on the water, such that the bulge, the moon is trying to pull the bulge kind of straight towards it, but the planet's spin wants to pull the bulge a little bit, the top bulge a little bit to the left. And so what we end up getting is that the bulges really look like this. So, it's still kind of going, facing the moon, but it's actually being pulled a little bit over this way in the direction of the planet's spin. And, the similar effect is visible at the other end. So, and again, this is a real effect, that we see here on Earth. And it gets even more interesting because this drag actually slows the rotation of the Earth, right? Because as the Earth is spinning, or any planet would be spinning, some of the energy of the spin is actually being kind of used up through friction, if you will, right? Because it's dragging or fighting against the water. So it actually causes the planet's spin to slow a little bit. And the Earth spins a little slower every day because of this. Again, it's tiny, right? But every 100 Earth years take about 2 milliseconds longer than the prior 100. So our Earth is slowly slowing down, right? But just by a really, really slow rate. And remember that we said gravity works both ways, right? So, we talked about how, the moon is pulling on the planet, but then, in this case here now, let's talk about how the planet is pulling on the moon. And so tides work in reverse, right? The planet's gravity creates bulges on the moon as well, and also slow down the spin of the moon. Just like, we just said for the planet, the same basic effect applies to the moon as well. And this has already happened in our system here with the Earth, right? The Earth has already slowed down our moon spin. So our moon has become what we say tidally locked. The moon is always showing the same side to the Earth. And it's kind of in this animation here, right? You can see that, the moon is always, I'm sorry, the center here, let's say that's the Earth, right? It's always looking at the side of the moon that has like these dark spots on it, right? So as the moon orbits, it's always showing the same face to the Earth. And that's because over time, the tidal forces have caused the moon's rotation to slow to the point where it actually became what we call tidally locked. But wait, there's still some more stuff to talk about. So um, the Earth's tidal bulges, turn out to pull on the moon a little bit, right? So now we've created these tidal bulges, and there's mass here, right? And so this mass has, again, every mass, any mass, creates some gravitational effect. So the tidal bulge mass creates some gravitational effect that the moon can feel. And so let's think about that, right? So we have our moon zipping around in its orbital path. And the primary action here is that just the overall mass of the planet is pulling the moon towards it. And like we said earlier, the moon doesn't actually crash down because it's also going through its orbital path, staying in a nicely balanced position there. But now let's see what's happening with these tidal bulges, right? So now I've got this extra mass that's kind of sitting here, right? And if you imagine that this bulge is pulling on the moon just a little bit, right? It turns out that it creates a small pull effectively in the direction of the moon's travel. So if you remember your physics or math from a long time ago, this is basically some vector math, right? So that ends up being a small force vector along the direction of the moon's orbital path. And so you can kind of think of it as maybe you can imagine there's like a rubber band, right? That's attached to this tidal bolt, right? And it's pulling the moon, most of the force is pulling it, of course, down, towards the planet, but then a little bit is pulling it forward, right? And that forward pull is actually causing the moon to speed up over time as it's going through its orbit. And in our particular case, in the Earth's moon, yeah, we can measure this. Our moon is receding from the Earth all the time. It is roughly receding at the rate at which your fingernails grow. So, imagine how much your fingernails grow in a year. The moon will be that much farther away next year in September. So quickly review this, right? Tides are the results of gravity differentials. Two objects orbiting each other exert tidal forces on each other. Then tidal forces create tidal bulges in water as well as the land, and they can cause objects spin or rotation rates to slow down, right? And in our case, our moon has already become tidally locked. They may also force objects, yeah, actually, I just said this, right? They may also force objects, the less massive one going first, to become tidally locked. And then they may slow orbital speed and distance. Sorry, may slowly increase orbital speeds and distance, just like our moon is slowly receding, from the Earth. And just like a moon may lock to its planet, a planet may actually lock to its star as well, right? So you have tidal effects between, let's say, the sun and Mercury, right? The planet closest to the sun. And it turns out, yes, Mercury has also experienced a form of tidal locking, to the sun. So these forces and these effects are very important because they happen all over and they drive a lot of the mechanics of the solar system. All right. So now then, armed with this general knowledge, let's talk about moons of the solar system's planets. So again, here's our kind of artist's rendition of what our solar system looks like, right? With Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and our little favorite here, Pluto over here. Now, again, the scale of this is really all wrong. So instead, let's look at this picture for a moment, right? Here, we see much more accurately how the planets are spaced out, for example, right? And one interesting takeaway from this picture is that the first four planets are actually really close to the sun compared to everything else, right? So there's a really relatively tight cluster, right, of Mercury, Venus, Earth, and Mars. Then there's the asteroid belt, and then things get really spread out. We say that the Earth over here is 1 astronomical unit away from the sun. It's just a measure of convenience. We just chose to call the Earth-Sun distance 1 astronomical unit. And then you can see here that Saturn is 10 astronomical units away. And if we go all the way to Pluto, it's almost 40 astronomical units away. So yeah, things really get spread out over here. And so yeah, we'll visit the moons of each of these guys. So before we do that, though, I have a question for you, right? So how many moons do you think we need to visit, right? So in your own minds, for a moment, you can pick one of these ranges, right? How many moons do you think we need to check out on our journey through the solar system? So I'll give you just 2 seconds here while I take a sip. So pick your range. Okay, well, what range did you pick? It turns out the answer is 420. So we have cataloged 420 moons in our solar system. So I hope you all went to the bathroom before we started because we're gonna be here a while. So first planet to visit is Mercury, and Mercury, I guess the first guy off the sun here, and this guy has no moons. That was quick. Okay, then we have Venus. Venus is our second planet from the sun, and Venus has no moons. Okay, so we have made zero progress so far towards our 420 moons, right? So let's see if the Earth does better. And of course, yep, third planet from the sun, and we know that the Earth has a moon, right? We see it all the time. And since this is our own moon, in a way, it's the most important one, right? So we'll talk about this one for a while here. So it's definitely part of our home. It's an important part of our cosmic neighborhood. And here's kind of an interesting perspective that we usually don't see, right? This picture here shows pretty well how far away the moon from the Earth really is, right? So this was taken by a spacecraft that, was flying away from the Earth-Moon system. And, it shows, there's an actual photograph. It shows the Earth and then there's the moon over here. Um, at some point in history, we had no idea how far the moon was really from the Earth. And some people thought, hey, maybe if I can just walk far enough past those mountains over there in the distance, maybe I can get close or even touch the moon. Not a completely crazy thought, right? If we don't understand astronomy, if we haven't had the benefit of all our scientific investigation. But today, of course, we know that, yeah, this is actually, quite the distance. So our moon is about 4.5 billion years old, just a little bit older, sorry, a little bit younger than the Earth. Its measurements are a mean radius of about 1,000 miles compared to the Earth's 4,000 miles, right? So the moon is about 4 times smaller in terms of diameter or radius than the Earth. Its gravity is 1/6, meaning that it would be much easier for me to jump up into space, right, into the air, or rather off the ground, I should say, if I were on the moon. And our moon is the fifth largest moon of the solar system. So that's quite respectable. Out of those 420, this one is the fifth largest. Its orbital period is, this actually gets a little complicated here, right? There are these two different terms I've used, sidereal and synodic. And so the first one here is if we look at the moon, the Earth moon system from the outside, let's say, you're an alien out in space, right? And you're looking down at the Earth moon system and you're tracking the moon's orbit around the Earth based on the background stars, looking at the background stars. If you do that, then yeah, you will see that it takes 27 days and change, right, for the moon to make one complete orbit around the Earth. But now, for those of us who are actually living on Earth, it looks a little different, right? Because the Earth is rotating also. So for us sitting on the Earth and looking up, to us, it actually appears that one orbit of the moon is 29 days and a half, right? Just because now we're combining the Earth's orbital path and speed with our Earth's rotation, right? And so we actually perceive an orbital period to be a little longer, than an alien who's just looking down from the outside, comparing the moon against the stars. And so this guy here, this 29 and a half days is a lunar month, right? Some cultures, in some places we go by lunar calendars, right? And you maybe track lunar months, and this is that lunar month. Okay, and our moon's parents were the Earth and another body, right? Most likely, this is the leading hypothesis for how our moon came to be, and so we've called this thing that came zipping at us from the outside Theia, and it crashed into the young Earth. Made a big impact. A bunch of junk got spewed off into space, temporarily forming a ring around the Earth, and then this accreted or coalesced into what we now have as our moon. So this is how our moon came to be. And of course, hobbies, our moon causes the Earth's tides. And it actually does so in collusion with the sun. So it turns out our tides are not just from the moon. The sun actually plays a pretty big role. And this is interesting, right? Because the moon is relatively close, 238,000 miles, whereas the sun is 93 million miles away. So almost 400 times farther away. But on the flip side, our moon is only 7.3 times 10 to the 22nd kilograms, and the sun is just way more massive. It's just much heavier. And, you don't have to do the math here, right? The sun is basically 27 million times more massive than the moon. So even though it is so much farther away, it is also so much more massive, such that the sun actually still has significant tidal effects on our Earth. In fact, it's about half of the tidal effect that the moon has. And so again, especially if you are in any way interested in nautical things, right, or have lived near the ocean, you may know that there are actually different kinds of tides, right? We talk about spring tides and neap tides. And so here is a diagram of, yeah, so here we have the sun and the moon, they're kind of in line. So here they're kind of pulling together. Their tidal forces are kind of adding up. And so here you would get especially big tidal bulges. But then over here, you have the sun, kind of pulling in one direction and the moon pulling in the other. And so these things kind of average out and you end up with a smaller tide, towards the moon direction. And then this would be, one of the neap tides. And so, yeah, so again, this tidal stuff is complicated, but we experience it here every day, on Earth. And it's an uh, important mechanism that we have to understand and live with every day. And technically, other bodies, like other nearby planets, really also exert tidal forces on the Earth, but really only the moon and sun have the right distance and mass combination to matter. The other bodies are effectively irrelevant. So you could argue that Venus, right, our neighboring planet, has some tidal effect on the Earth, and technically it does, but they're just so tiny that they are irrelevant. Okay, now let me ask you, do you ever feel a little insecure about your backside? Kind of like, do these jeans make my butt look fat? Right? And it turns out that the moon feels a little insecure about its backside, right? Because we always just see, what we kind of consider the front, right? This is always how we see the moon whenever we look into the night sky. Now, but of course, there's a backside, right? And the backside looks like this. And we can see this through the benefit of spacecraft, right? We can send equipment out into space to take pictures for us. And this is then what we see. And we already know why this happens, right? We actually talked about this. This is this tidal locking again, just to do a callback to the earlier conversation where, the tidal forces over time cause the moon's rotation to slow to the point where it now rotates such that it always shows the exact same face, to us here on Earth. You may notice the two sides look pretty different, right? So the near side and the far side, they clearly have different geology, right? They have a different surface structure. And here is, you know, that same thing, but kind of shown to highlight the topography. So the green is kind of the reference, and then you can see it goes all the way down to -6 kilometers in like these purplish regions, all the way up to +7 kilometers, like in these red regions. So the far side has these really big variations in landscape, right? From like 13 kilometers range, like from here to here. Whereas the near side that we see, it's relatively more flat, and a lot less bumpy, if you will, right, than the far side. And we can clearly highlight that there's something going on here, right? There are these low, dark, pretty smooth regions, that we get to see from our vantage point on Earth. And these are what are called the Maria, or singular is mare, right? These regions were originally thought to be seas, oceans. This is when, we didn't have very good telescopes. People looked at the moon and they could tell that there's something different there, right? And they thought maybe there are oceans of water there. Now, of course, we understand that it's something different. So the Maria cover about 15% of the moon's surface, and there are regions where lava filled impact craters, and then the lava kind of filled it, was kind of sloshy at some point, and then cooled into a relatively smooth surface. And we can assess that this happened around 3.5 billion years ago, compared to the moon's overall age of about 4.5 billion years. And the Maria look a little darker due to slightly higher iron content, in the rock there. And here's a map of the moon. We've labeled all this stuff. Don't worry, you don't need to read all this or memorize it all. But some people like to really really know the moon, and you can see that the different mare, we've given them different names, and the craters have been given different names, and so we have a pretty detailed story for ourselves of what's what on the moon. And of course, we've gone to the moon, right? We've had a crewed space mission over 50 years ago now, right? But we've been there 6 times, Apollo 11, 12, 14, 15, 16, and 17. These were all missions that have landed humans on the moon in these locations. And people sometimes ask whether we can see these, through our ground-based telescopes, and the answer is no. So the evidence we left there, it's just too small for our ground-based telescopes to resolve. But we've sent satellites to the moon, specifically something called the Lunar Reconnaissance Orbiter, a satellite that goes around the moon, orbits the moon, and then it takes pictures, high-resolution pictures. And there we can see what we've left up there, right? So here's Apollo 11. Here's the lunar module stuff that's left over. You can see tracks where they cruised around, in the rover, and same thing for these other places. So, yep, we really have been on the moon, and we can see where we went. And you might ask the questions like, well, we talked about how the two sides are different, and why are they different? And it turns out we're not so sure. When I researched this, we have hypotheses. By we, I mean, scientists that think about the moon, but we don't have a definitive story yet on why the two sides look so different. So, hey, if there's anybody out there, especially young people in the audience, you could be somebody who helps figure out, what went on here. Our internal structure, the internal structure of the moon, is it's not quite as boring as you might think. There is actually, still a hot core, although, it is not nearly as interesting as the Earth, because the Earth has a lot more different layers and a lot more cooking. But yeah, even the moon has, an inner core, where there is still a lot of heat stored that's slowly leaking out. Yeah. Okay, here are some moon facts, and for each of you, each of you can kind of decide in your own head whether these are true or false. So ready? Let's see. So first, the moon is visible only at night. In your own mind here, true or false? The moon's image is larger at the horizon than at the zenith. Is that true or false? The moon has a dark side. The moon does not spin on its axis. The moon's phase, like half moon, they are caused by the Earth's shadow on the moon. And during a supermoon, the moon is huge in the sky. And then emergency rooms are busiest during full moons, and the moon is made of cheese. So let's talk about the first one. The moon is visible only at night. And the answer is no, it isn't. Right? Sometimes people actually think that because they just never noticed. But the moon is actually up in the sky during the day. It happens every month, right? And here's a photograph of it. And here's another one, right? So here's the moon during the day. And yeah, if we look at the lunar cycle, we say that the moon is generally visible during the day, during what we call first and third quarter moon. So, and I'll explain that a little bit more in a bit. But yeah, go look for it. It's up there. And to go back to this picture, the lit side of the moon here, right, is pointing towards the sun. The sun is over here in this picture, and yeah, because the sun is what's lighting up that half of the moon, right? So the lit part of the moon will always be kind of pointing towards the sun. Okay, the moon's image is larger at the horizon than at the zenith, right? Zenith being the point overhead. And this is a very common idea, right? Because the moon often does look really big when it is rising, when it's close to the horizon, just hovering over some houses or something like that. But I got bad news for you. This is just an illusion, right? Regardless of how convincing it seems. And you can check this for yourself, right? So you can hold out your arm, and you can look at your fingernail, right? Your little fingernail, and you can compare the size of your fingernail against the moon. And do that when it's at the horizon, near the horizon, and when it's overhead. And you'll see that the moon size is the same, right, compared to your fingernail, regardless of whether it's, over the horizon or overhead. Okay. So it will not change, the moon doesn't really change size regardless of its position, right? And this is homework for the next full moon, which is actually just in a few days. So you can do that check very soon. And the mechanism for this moon illusion is subject to some debate. It's basically psychology, right? And it may have multiple causes. But one way we can think about it is an object's perceived size can be different based on its surroundings. And here's one of those visual illusions, right? This dot, that's sitting inside the big dots looks smaller than this guy that's surrounded by small dots. And if we make this the moon, here's the moon. Yeah, I can move this over here, exactly the same size. But still our brains perceive it a little bit differently in size based on its surroundings. Or it could be a perspective thing, right? So these are also the same moon, but even to me, even though I know what's going on, looking at it right now, these don't look exactly the same size to me, right? Because just our brains play tricks sometimes, right? And our perception is not perfect, and the context in which we see something matters. All right. The moon has a dark side. This is also a common statement, and even title of a Pink Floyd album. But there is no dark side, right? There's just the far side, and we saw this earlier, right? We can see this part, with spacecraft, and the far side still receives sunlight as the moon goes through its orbital cycle. Okay, so yeah, no dark side. And then sometimes people think the moon does not spin on its axis. In fact, I literally just came across somebody making this claim on YouTube or somewhere, right? But sure, it spins on its axis, right? We just don't see it spinning because we always just see the near side, right? And this is again, back to this thing, right? Tidal locking. So the moon is rotating around its own axis. It's just that its rotation rate matches its orbital speed. And so again, we always just see the same thing, right? But the moon does actually rotate on its axis. Okay, the moon's phases, like half moon, are caused by the Earth's shadows on the moon. Um, and the answer here is no, that's not what happens, right? So, here are the phases of the moon, right? So there's new moon and we actually don't see it. And then, we get like a crescent moon, a half moon, then it goes to full moon, and then we kind of go back around. But what is happening here? This is all a consequence of kind of angles. So let's think about this a little bit. So let's put ourselves the sun over here, right? And sunlight is coming this way, towards the Earth. And if I now, put a moon around it, notice that, of course, the side of the moon that will get lit up is always the one that's facing the sun, right? But then we're looking at it from our perspective on the Earth, right? So if the moon is kind of between the Earth and the sun, then I'm looking at the dark part of the moon, right? Whereas if I'm looking here at the moon on this side, right, I'm looking at the light part of the moon, or if I'm here, right, I'm seeing, a half moon. So I hope that makes sense, right? So it's really a function of just kind of geometry of the orbital paths, right? Here most significantly, right, this is not appearing dark to us because the Earth is casting a shadow. It's appearing dark because the sun is lighting up the other side only. But are there cases where we have the Earth's shadow on the moon? And the answer is yes, during lunar eclipses. So here's an example of like a lunar eclipse. We have full moon, and then slowly you have the Earth shadow actually creeping over the moon. And then during the actual eclipse, the moon often looks, really reddish, right? And in fact, we call that a blood moon sometimes, right? So these are the shadows, right? And then this is the blood moon, and it looks red because uh, there's still light filtering around the Earth. Sunlight hits the Earth, partly goes around, and through the atmosphere, and it's that residual light through the Earth's atmosphere that lights up the moon a little bit. And it looks orange for the same reason that sunsets look orange, right? And turns out we actually have a blood moon coming up, I think, just on the 7th, but we don't get to see it here. But the folks living in Asia, I think, East Africa, Australia, I think, right? They'll get to see a nice blood moon eclipse like this just in a few days. Um, let's kind of see a little more about how this is working, right? So why do we sometimes get these eclipses, right? Even though most of the moon's phase, like half moon and all that, are just other effects, right? Well, it's all about orbital planes, right? And so here's our picture from before. We have our sun, let's say we have the Earth here, and the moon going around the Earth. So in fact, yeah, here we'll just made it ours, right? So these are specifically sun, Earth, and moon. And now we'll just tilt our perspective a little bit, so we're not looking at it top down anymore. We're looking at it a little bit at an angle. And now we'll zoom in a little bit just to make it easier to see. And now I've tilted the moon's orbit a little bit, right? Before the plane of the planet going around the sun was the same as the plane of the moon going around the Earth. But now I've tilted the Earth moon orbital plane a little bit. And it turns out our moon is doing this, right? Our moon's orbital plane is tilted about 5 degrees from the orbital plane of the Earth Sun system. And so what can happen here is that sunlight can hit the moon even when the Earth is between the moon and the sun, right? So in fact, that's kind of the arrangement we have here, right? So the way I've drawn it right here, we're not getting a lunar eclipse. We're actually getting a full moon, right? Because sunlight from the Earth is easily able to bypass the Earth here and hit the moon and then reflect back, and we see a full moon, right? So this is how we see a full moon, even though the Earth is between the moon and the sun, so to speak, but it's not exactly in between. But so here's another picture of this, just at different portions of the whole orbital cycle system. And yeah, so this is basically what we just had in the prior picture, right? So here the moon is below the Sun-Earth orbital plane. This looks like a full moon to us. This here looks like a new moon, right? Where we just see the backside of the moon, while this side is lit up. And these are just our normal monthly phase cycles. But if we end up in a spot like this, here we get an eclipse, right? So it turns out that here the moon is between the Earth and the sun, right at the point where we're also in the orbital plane of the Earth around the sun, right? So here the moon is literally sitting between the Earth and sun, and we get a solar eclipse, right? This is where the moon blocks out the sun. Or over here, we would get a lunar eclipse. And just to kind of show this a little bit more zoomed in, again, here there are no eclipses because the moon is above or below the Earth-Sun orbital plane. And here, we actually get eclipses because the moon just happens to, pass through the Sun-Earth orbital plane, and either the sun blocks the moon or the moon, eclipses. I'm sorry, the Earth blocks light from the moon, eclipsing the moon. So it's all about geometry and angles of view. And, for the most part, there are no shadows involved unless we are specifically talking about an eclipse. Okay, during a supermoon, the moon is huge. Well, is it? So again, here's our picture of orbital diagram, right, of orbital paths. And it turns out that I've been drawing this as a circle, but really orbital paths tend to be ellipses. A circle is a special case of an ellipse, but the moon's orbital path around the Earth is actually an ellipse. And there are some terms we have to introduce called perigee and apogee, right? Because if you're talking about this being an ellipse, sometimes the moon is closer and sometimes the moon will be farther, right? And so, yeah, so perigee is the closest point, apogee is the farthest point, and the closest distance then at perigee is about 225,000 miles. And at the farthest distance, it's about 25,000 or 26,000 miles farther, right? And we have an average distance of 238. So usually when we talk about Earth-Moon distance, we tend to, give the average, but actually it wobbles, between these two numbers. And so at perigee, when the moon is closest, it actually appears about 12% larger and up to 30% brighter. And here's just kind of the same thing again in the diagram form, right? Sometimes the moon is closer at perigee, sometimes it's farther at apogee. And this is how it would kind of appear in the sky then, right? So the it appears 12% smaller when it's at its farthest distance and 12% larger, just flipping it around, right, when it's at its closest. Now, is it huge? And would we really notice if news media wouldn't be putting all kinds of headlines out about the moon being a supermoon? I don't know. So it is real, but I wouldn't call it huge. Um, but what happens during a supermoon? Not much. A lot of articles sometimes get written about all kind of crazy stuff happening, but really, I would call these articles of questionable value, right? Supermoon is really just an astrology term. Astronomy and astrology are not the same thing, right? And so the innocent supermoon may be falsely blamed for increased earthquakes or volcanic eruptions or something like that. But really, the moon is getting a bad rap. It really had nothing to do with any of this. And kind of related to this, often people perceive or say that emergency room visits, for example, are up, during full moons. Are there more psychiatric symptoms, more epileptic seizures during full moons? And the answer is no. Formal studies show that there's really no correlation between full moon nights and incidents like emergency room visits. Now, why do people nevertheless think so? And it's because of a psychological effect called confirmation bias, right? And the short version of this is that we have an idea in our head, we look for and remember confirming evidence, and we ignore or forget disconfirming evidence. And this is actually a really important concept because it doesn't come up only in this moon context, right? But it comes up all the time in our lives, right? And if you want to read more about this stuff, here's a book you could look up, right? The Skeptic's Guide to the Universe. Lots of cool content about confirmation bias and other critical thinking tools. I recommend it if you have not come across this. And then finally, the moon is made of cheese, and it's not. You probably knew this one, right? The moon is actually made of rocks that are different by region. The Maria and the highlands have, different types of rock. Basalt, which is iron-rich volcanic rock, is what you mostly find in the Maria. And then the other parts are, I don't even know how to say this, mafic plutonic. I don't know. Any geologists in the audience, you can help me later how to pronounce this properly. And when I tried to research this, you can go into a rabbit hole of all kinds of different types of rock. And I don't want to bore you with this here, but one term I do want to introduce is this term called regolith, because you hear that a lot, I think, when you hear about the moon. And regolith is loose dust and rocks that are covering a solid rock underneath. And so our moon and many moons have a layer of this regolith. And then you also hear the term igneous rock, which is solidified lava or magma, and that's really most of the moon's surface with this regolith on top. In contrast, most of the Earth's rock is something we call sedimentary rock, right? So there are fundamental differences between the geologies of these different places. And again, if you're a geologist, this goes, a million layers deep in terms of complexity, but we'll leave it here for today. So no cheese on the moon, but if you want to read a book about what might happen if the moon were to turn to cheese, you can read this science fiction novel. That was kind of fun. So you could check that out. But the conclusion here is that all these guys are false. So I don't know if you're bored with our moon yet, but too bad. There's a couple more things I want to say before we go off to other moons. An important term that comes up in the context of our moon is albedo. Albedo is the fraction of sunlight that's diffusely reflected by a body like our moon. And we often think of the moon as being really bright, and I think so too. It appears very bright. But the moon's albedo is actually lower than one might think. We say it's 14%, so it only reflects like 14% of the sunlight that's bouncing off it. And really, that's just brighter than slightly worn asphalt. But because the moon is sitting in the black background sky, we perceive it as quite bright. Another cool thing is this thing called libration. You know how we said that we only see half of the moon? Well, turns out we actually see about 59% of the moon. And this is because of, our ellipsis and orbital tilt, right? And this is, if you really look at the moon closely during its monthly cycle, this is actually what you would see. Notice how it's wobbling a little bit, and it's like, wee, it's gyrating a little bit. And so through that, we actually get to see 59% of it. And this is an interesting example of how in science there's always almost always more depth than you think, right? You explain things to a certain level, and then you can go a little farther, right? A little further if you want, and there's more complexity and more interesting stuff to find. And one way to kind of imagine what's happening here is that going back to this diagram, right? Yeah, imagine we're sitting here on the Earth and we're looking, we're looking at the moon. Notice that, here, this full moon, if you're standing here, you're kind of looking a little more at the top of it, right? You're getting to see it a little bit from the top. Whereas we look at this full moon, now we get to look at it a little bit from the bottom. And so this is part of why we see this wobble, and over time get to see 59%, right? So that is what's giving us this libration behavior. Okay. Uh, Briefly talk about atmosphere, right? So on the Earth, we have an atmosphere. It's good. It keeps us breathing, right? The layers are troposphere, stratosphere, mesosphere, thermosphere, and exosphere, and that's kind of in this direction. Clouds are sitting here in the troposphere. Weather balloons are sitting in the stratosphere. The aurora, right? They appear over here in the thermosphere. And then there's this final thing we call the exosphere. The moon only has this exosphere thing. So an exosphere is essentially a place where you have small particles. Um, these particles, like molecules, they're still gravitationally bound to the body, like to the moon or the Earth, if you look at the Earth example. But the density of stuff is so low that a particle is going to be zipping around and it's not really going to hit anything else, right? It's a super low density environment. And so the moon's exosphere is essentially immediately above the moon's surface, right? For all practical purposes, the moon's surface is a vacuum because all this stuff doesn't exist, but right at the exosphere. And the exosphere is largely radon and helium from radioactive decay and tiny particles that are knocked loose by micrometeorites that whack into the Earth's surface. Um, but yeah, so technically there is an atmosphere on the moon, but it's this exosphere thing that's certainly nothing that anybody could breathe. And for all practical purposes, it is kind of a vacuum. So there is no atmosphere to trap heat on the moon, right? Or have any other weather. And as a result, the only heating and cooling is just through radiation from the sun. And these cycles occur very rapidly. And at the equator, man, it gets pretty hot, 121 degrees C, way hotter than water boiling. Or it gets super cold during the dark phase, right? Where it's, minus 133 C. And the lowest extreme temperature is almost minus 250 C or 410 F. So pretty cold. And the moon experiences moonquakes. The Apollo mission left seismometers on the moon to measure them, and they occur at different depths, and we know they occur for different reasons. For example, the moon is shrinking as its interior cools. Things hit it, right, and that can cause a quake. And there can also be thermal expansion and contraction as the moon goes through its dramatic day-night cycle with its really different temperatures. And we looked for water on the moon, right? And the Apollo missions didn't find any water. Not until 2009 was there any reasonable evidence that there might be water there because we were able to detect, H and O, hydrogen and oxygen atoms, from water splitting. And we actually saw some ice when we intentionally hit the moon with a projectile and watched what flew up. And it's like, hey, there seems to be ice there. And various NASA missions have found more evidence of water, since then. So remember that, it gets up to 121 degrees C on the moon, right? So water would boil away at that temperature. But water ice may be present in parts of craters that are always in shadow, right? So there could be parts of the crater, and there are parts of craters where the sunlight never quite reaches. And so ice could be present there. And then a mission in 2020 also found that there's actually water in sunlit areas, but that water is locked inside grains of soil. And it's quite a lot, right? Like a 12-ounce bottle of water in a cubic meter of soil. That's quite a bit. And this is really important because if we want to either just, visit briefly on the moon or establish a permanent presence, we need water, right? We need it for drinking and sanitation. If we want to hang out longer, we need it for growing crops and for cooking. And if we have water, we can make oxygen out of it and breathe it, right? So we can convert H2O into H and O, hydrogen and oxygen, right? We can take the water molecules, add energy like from solar panels, and we can make oxygen and hydrogen out of it. And if we have this stuff, we can also make rocket fuel from it, for example. And these things are super useful for lots of other industrial processes. So water is just a key ingredient that we need to hang out on the moon. And we know that there is water up there for us to get if we work on it. I don't know if this looks like anything to anybody. This is from a science fiction show in the um, 70s, gosh, a long time ago, right? It was called Space 1999, when 1999 was still far in the future. And the premise of the show was that there's a base on the moon, which is not so dumb of an idea. Um, but a lot of other stuff around this show was complete nonsense, right? But this base idea, actually pretty good. And it turns out that NASA is planning a base on the moon with the Artemis 4 mission. And presence establishing a presence on the moon poses many challenges and risks, like source of water, source of energy, and how do you make a radiation-proof shelter? Because it turns out almost all science fiction stories gloss over the dangers of radiation in space. There's ionizing radiation, which means it's radiation that can break chemical bonds. And this radiation is in the form of like high energy protons and alpha particles from the sun and from outer space. And these things can be bad, right? But it turns out on Earth, we are sufficiently protected through our magnetic field and our atmosphere, deflecting and absorbing this radiation, which by the way gives us the aurora, right? This is our atmosphere and magnetic field in action, keeping us safe, and giving us a pretty light show in the process. Um, but without this protection, this radiation can be fatal. So the moon has no atmosphere or magnetic field to keep us safe. So we could build shielding, but it would be very expensive to do. So what about structures that are already there? And it turns out there are things, like lava tubes up there. I'm not sure if anybody here in the audience has, gone to check out a lava tube. This is a picture of a lava tube in Hawaii. And what you get is a volcano erupting, lava flows, the sides and top of the flow cool, lava continues to flow inside, and then the flow stops and drains out, and you have a cave left over. And it turns out, if you have one of those things, you can close it off, pressurize it, and boom, you've got a habitat. Okay, maybe a few more things to do, but it gives you a great starting point. And it turns out we have seen these structures on the moon that sure look like an entry way to a lava tube, and there are other geological features that strongly suggest lava tubes are present. And they could provide protection against radiation, meteorite impacts, and the temperature variations. So these tubes are huge in some places, it seems, right? And quite deep and could give us stable temperatures like minus 20 C or minus 4 F. That's actually not that cold. We could live there, especially if we apply technology to it. And there are missions proposed to explore. So a base on the moon, probably wouldn't look like, it did from that old science fiction show, but, we might start here to build it. And let's say goodbye to our moon here, and let's kind of go on to Mars.
Hey
And
Wolf, can I
yes, sir.
make a quick
Sure.
plug? So you were
Plug, yes.
talking about all these things that we would need to do to survive on the moon,
Hmm.
and this Saturday after our
Ah,
board meeting at 7:30, we have
yes.
a whole talk dedicated to the challenges of crewed long duration exploration missions to the moon and Mars with the track. I think that'll talk about all kinds of stuff related to what you just mentioned.
Thank you. Yes.
Yeah.
Good point.
So that's a free public talk, 7:30 on Saturday that anyone is welcome to attend.
Yep. Okay, if we visit Mars quickly here, so Mars is the fourth planet out from the center, and it has two what I call space potatoes, but technically they are moons, Phobos and Deimos. So they're not big enough for gravity to shape them into spheres. Um, this guy here, Phobos, was discovered in 1877, named after after Ares, the Greek counterpart of the Roman god Mars, and Phobos means fear. And there is a um, that's kind of an interesting theme here that you'll see with other moons. Sometimes we name these things after kind of it's kind of darkly themed. This is the moon that's closest to Mars. I'm sorry, excuse me. I just no, yeah, here we go. It's the moon closest to Mars and larger than its brother, and it's likely a rubble pile with just a thin outer crust. And its orbital period is really fast, 7 hours, 39 minutes. This thing is zipping around Mars quite frequently, and you could be standing on the Martian surface and see this thing come by multiple times a day. And it actually gets closer to Mars by a couple of centimeters every day, and eventually will break up and form a ring. Deimos, the other guy, right, discovered in the same place and time by the same person, named after the other son of Ares, and Deimos means dread. And It's farther away from Mars, a little smaller than the first guy, takes longer to go around Mars and is receding from Mars and will eventually escape. And so no two potatoes are alike, right? So different surface color and texture here. They suggest different chemistry and internal structure, right? So yeah, so all these things have a lot of interesting details about them. I should point out here that space potato is not an actual science term, but I'll use it a lot here. And but please don't go later telling people that I taught you all about space potatoes. So Jupiter is our next planet in the sequence here. So we have Jupiter, and Jupiter has 95 moons, and we're probably still counting. But there are four big ones, and then lots of space potatoes. And the four big ones are famous as the Galilean moons. So Galileo discovered these, when he was doing astronomy with one of, his home-built telescopes. And, his telescope, is worse than anything that we can build today, but nevertheless, he used it to do, great science. And his observations of Jupiter contributed to the acceptance of heliocentrism, the idea that the sun is in the center of our solar system. And here's a kind of a rendering of him looking off at the sky doing what he was doing. And here's a time-lapse animation of looking at Jupiter and watching the moon. This was taken from a spacecraft, but Galileo would have seen something similar observing over a long time, right? With Galileo's with the Galilean moons orbiting Jupiter. And so this is what drove home the point that, yeah, things definitely orbit, not just around Earth, but around other things. And so therefore, maybe, the Earth is actually going around the sun. So here are the four moons, Io, Europa, Ganymede, and Callisto. And there's a trick to help you memorize the sequence. And we say, I eat green caterpillars, right? So Io for, I for Io, eat for Europa, G for Ganymede, and caterpillars for Callisto. These are the moons from the inside out. Okay. And, they're named after a whole bunch of, again, Greek mythology. And so we're not going to read all this. You can read up on it. It's fun stuff if you like, but essentially the names all come from Greek mythology. So Io here is slightly larger than Earth's moon. It's the densest moon in the solar system, tightly locked to Jupiter, and has many active volcanoes that are spewing sulfur compounds. And the plumes can get really, really high, 300 miles high. And this is why the surface looks so yellow. It's that sulfur. And some of the mountains that have formed here are taller than, Mount Everest, the tallest mountain here on Earth. And this guy is also quite fast, right? Its orbital period is 1.8 days. And if we look at it through a telescope during the observing night, you can often see this guy move and change position, just in one night's observing session. Europa, the next moon out, is slightly smaller than Earth's moon, least massive moon of Jupiter, also tidally locked. And this is its surface is water ice with a liquid ocean underneath. Now, it is really too far from the sun for the sun to keep that water liquid. So the energy for the liquid water comes from tidal flexing, right? Earlier we said how tidal forces can actually stretch not just the water around the planet, but the planet itself. And so you have tidal forces kind of kneading the structure of this moon, imparting energy, keeping some water inside liquid. And there's some evidence of cryovolcanoes, which are volcanoes that are spewing water ice, into space. And so, we have an idea that this thing might have life in its oceans, right? So here's kind of a cross-section of it, right? Icy shell, ocean underneath, and then a rocky interior. And the amount of liquid water estimated to be there is twice that of Earth's, right? So more liquid water on Europa than here on Earth. And liquid water greatly facilitates chemical reactions and may have allowed life to arise and evolve. And so here's again a picture of the ocean, the ice shell, with a cryovolcano spewing water that turns the ice into space. And there's a NASA mission that is actually on its way to check this out. It launched last year. It's going to get there in 2030 and then do science for 3-4 years. And we'll see what we learn. Ganymede is the next moon. It's the largest and most massive moon of the solar system. It is larger but less massive than Mercury. And yeah, it's mostly rocks and water. And also probably has a subsurface ocean. Has a really thin oxygen atmosphere, actually. Nothing we could breathe, but there's something. And it's the only moon to have a magnetic field. Again, the energy for that comes from tidal forces. And again, we think there's an ocean under its surface there. Callisto's the next one out, and the second largest moon of Jupiter is the oldest and most cratered surface in the solar system. There's no geologic activity, so this thing is basically a dead world. But it may also have a subsurface ocean of sorts and a very thin atmosphere of carbon dioxide. Here's a family photo, right? You have the four moons of Jupiter hanging out with its parent. You would never see them like this through a telescope. This is just a composite, but it kind of shows you what they look like. And it kind of drives home the point you don't have to look alike to be part of the same family, right? So all of these guys are part of the Jupiter family, but clearly their chemistry and geologic features are all very, very different. And there's this idea of orbital resonance where, it's kind of a fancy version of tidal locking. You have a situation where for every one orbit of Io, Europa goes around exactly twice, and Ganymede goes around exactly four times. And yeah, so this is an interesting effect caused by gravity and tidal effects. And then, we have all the potato salad, right? All the other space potatoes zipping around Jupiter, much farther out. So it's a big mess of space potatoes. If you visit Saturn, we're now over here, and 274 moons, also probably still counting, seven spherical ones, and three of those are, quite notable. And, these guys are named in association with the Roman god of agriculture and harvest. And I guess that guy had other jobs too. And so the three notable ones, Enceladus, Titan, and Iapetus. And so the inner part of Saturn looks like this. You can see there's some moons here, and all the big ones are actually hanging out much farther, to the right. And we know this because, among other things, because we've had a space mission there for 13 years, the Cassini probe, that taught us a lot about Saturn and its moons, including Enceladus, which is the second smallest moon of Saturn, also tidally locked. And it is quite geologically active and also has a subsurface ocean. And the energy here comes from this orbital resonance thing we mentioned just a moment ago. And so we have actually observed these cryovolcanoes, right? So we can see that there is, water ice spewing off into space, squeezing through that ice crust. And there is this, again, so here's the ice crust and some liquid water underneath. And the idea here is that there may be geothermal vents underneath. So on Earth, we know these things exist. And this is a picture of a geothermal vent on Earth where there is, hot gases emerging from the ocean floor. There's an idea that Enceladus may have this. And this could also be a possible place to find life because we certainly know that on Earth, these are very rich areas of life in our environment. Titan is the next biggest moon out, largest moon of Saturn, second largest in the solar system, and it has a rocky core surrounded by water and layers of ice. And most significantly, it has an atmosphere, the most significant atmosphere of any moon. It's mostly nitrogen and methane, and it's much thicker than Earth's atmosphere. And it actually has weather, with clouds. And it's the only object besides Earth to have liquid on its surface. Here's kind of a diagram of what it would look like. Again, there is liquid water and then, its surface around. This is the atmosphere imaged by a probe that we sent there many decades ago. And we believe that, or we have a good idea that the atmosphere, looks something like this. There's methane here, then there are thick clouds, and then, nitrogen, methane, argon here, compared to our Earth's atmosphere. Notice that the atmosphere is much thicker, right? This is 500 kilometers thick, whereas the Earth's atmosphere is like 50 kilometers thick at this point. And so, yeah, we can certainly see lots of clouds looking at Titan. And we know that there's methane rain producing lakes, and there's wind that creates surface features like dunes. And here are pictures through with thermal imaging of the Titan surface. And if we kind of unroll that into a flat sheet, just to look at its surface like a map, these blue regions are the lakes, methane lakes. And for example, these purple regions are sand dunes, that are being blown around. So this is all quite exciting up there. And here's a snippet of its surface imaged by one of the probes. And one of the cool facts here is that the atmosphere and gravity are such that a human with artificial wings might fly. The atmosphere is 1.5 denser than Earth's, and the gravity is about a sixth of Earth, right? But in reality, it's super cold, so you'd freeze. Don't go there, but it's still fun to think about. Iapetus is kind of the last one we'll visit here, and it kind of has this this dirty spot here, right? It's mostly water ice, but it has this dirty side because something whacked it and hit it, at some point in the past. And then, just an honorable mention is our Death Star moon, right? Mostly water ice. And it actually is partly responsible for, the rings. There's a lot of fun stuff we could talk about, with regard to Saturn's rings, but that's for another day. And then these are the other three, Roman named moons. If we go to Uranus, we're now out here, and there are 27 moons, five large spherical ones, and then lots of space potatoes. So these guys are named after Greek mythology or Shakespeare, and they're all pretty similar in composition, and they're likely formed by just accretion, from the same stuff that made Uranus. And here's the space potato, and then here are the five, spherical moons. And for the most part, that's kind of a theme here, right? Rocky center, some liquid water, and an ice shell. Only Miranda doesn't seem to have any kind of liquid water on it. If we check out Neptune here, now we're over here in our solar system. Total is 16 moons, one spherical, one called Triton, lots of potatoes. And these guys are named after Greek mythology. And here is Triton, this one moon. And it is tidal locked to Neptune. It has a thin, mostly nitrogen atmosphere with clouds and haze. It's mostly water ice. It may have an ocean again, right? But the interesting fact here is it has more than 99% of all the other moons of Neptune. So this is quite a chonker compared to all the other moons that are around Neptune. And furthermore, it has this idea of a retrograde orbit. Its orbital direction is opposite Neptune's spin. So Neptune is spinning one way, and the moon is actually orbiting the other way. This is very unusual, and this suggests uh, that the Triton was likely captured as something that originally flew by Neptune and was caught in Neptune's orbit and was captured into the orbit. And this probably created a big mess. Whatever moons were there at the time probably caused them to be ejected. And now we just see kind of the leftovers from that capture event. And then here, this is like the biggest space potato, just as an honorable mention. It's almost managed to be spherical, but not quite massive enough to be so. And then let's quickly we'll visit Pluto, and then we'll wrap up for the day here. So now we made it all the way out here. And so Pluto has a total of five moons. One spherical one is called Charon, named after the ferryman who carried souls to the underworld in Greek mythology. And Pluto, right, the parent planet, is the Roman god of the underworld. So again, kind of dark themes here and how these things are named. And that kind of continues on with the names for the space potatoes here. Um, but yeah, Charon is the star of the show. So here it is, right? This is the big guy, and then here are the space potatoes, right? So Charon, you can see, is a much bigger moon extending off the screen. And one thing that makes it interesting is that it is very large relative to Pluto, like half the diameter and an eighth of the mass. And it's like rock and ice, about half and half. And Pluto and Charon have a special relationship, right? And to understand that, we have to talk about very briefly about a thing called the barycenter, which is the center of mass of two orbiting objects. Usually, like one object is much more massive than the other. Like, the Earth is much more massive than our own moon. Okay. And then the barycenter is inside the more massive object. And the more massive object kind of wobbles just a little bit, while the smaller object does really almost all the visible work of orbiting, kind of like this. So this could be the Earth, this could be our moon, and our Earth actually wobbles just a little bit as the moon orbits, but the moon is doing most of the visible work of orbiting. But you could have a case where the two bodies are much more similar in mass, and then they're really orbiting a point that is sitting in between them. And that is what Pluto and Charon are doing, right? So they're similar enough in size that their orbital center, their barycenter, is between them. And so they're really orbiting each other rather than, kind of one orbiting another. And so here, it's kind of the size and distance to scale. They're pretty similar. They're pretty close. And here's an animation of what's actually happening, right? So you can see that they're both orbiting kind of a point in between them. And they are mutually tidally locked, always facing each other with the same sides. And with that, let's go ahead and wrap this up. Okay. We said that moons are natural satellites around planets or other moons. A moon can appear in a variety of ways, right? Through accretion or collisions, through capture, things like that. Each moon is a different, unique world, and some are also space potatoes. Tidal forces drive many effects in a planet-moon relationship. So this is really important to understand. And some moons in our solar system, may harbor life, like Enceladus or Europa. So that is pretty exciting. Here's a quick picture of the various moons we visited. Again, our Earth here was the fifth largest. Few are bigger, and a lot of them are smaller. And yeah, astronomy is a big field, right? So there's so many things about it, many different facets. Our solar system has a lot going on with a lot still to be explored. And there's more wonder and mystery that lie beyond our solar system as well, right? And you have many resources to learn more about moons and everything else. And again, if you want to visit us for another different talk in the future, we'll help you with that, or there are lots of resources out there. And we'll put a handout in the chat here, which has some information on other offerings of SJA you can check it out. So I don't want to bore you with reading this, but go check it out and visit us in the future. And if you want to volunteer to help us run the club, we can always use help. Or if you're not in the neighborhood here, just go ahead and find your local astronomy club and hang out with those guys. And I'll just kind of close on saying that, science is our tool for unlocking the universe. There's stuff we know, stuff we don't know yet. There's a lot that remains to be discovered, and you can help. There's citizen science projects, there's some in the handouts, or if you're a young person, especially, you could become a scientist, and then you can help us, get over here. And if you want to watch some TV, there's a fun show for all mankind that explores a different history of the moon missions and the space race. So this is on Apple TV. This can just be a fun diversion. And with that, I'll say thanks for listening. And yeah, if you have any, final questions or anything, I realize I talked a little bit too much and ran a little bit over, but thanks for hanging on. I hope this was interesting. And if there are any final questions, we can visit those.